Hello everyone. In this video, I'm going to be discussing basic trigonometric identities. Identity, recall, is an equation that holds for all values of a variable, or variables, whatever the case may be. And unlike equations that we might be used to normally, these are not equations that you solve for anything because it's true no matter the value of the variable. It's an identity. Both sides are identical. So, a basic example of an identity is that x plus x is 2x. That is certainly true no matter what the value is for x. Okay, so with that stated, let's talk about cosine and sine, the basic trigonometric functions. And as we have been discussing in class, the cosine and sine come about from the following sort of construction. You start with an angle with a particular angle measure, theta, we'll use here as the variable name. We use the initial side of the angle as the x-axis. So wherever this angle might be in the plane, we can scoot it over so that the initial side is along the x-axis. And furthermore, we can make it so that the vertex, which is this point right there, is at the origin. And then what we do is we draw a unit circle centered right at the origin. Unit circle meaning radius 1. And then we see where the terminal side intersects with that unit circle. That done, the x-coordinate of that point is known as the cosine of the angle theta, and the y-coordinate is known as the sine of the angle theta. Okay, so we are going to look at some identities that we can get from basic geometric reasoning of this picture. So the first one, there's really not much to do here. It's that if you take an angle and you add 2 pi to it, it does not change the values of the sine or the cosine. And so one point of view here is that 2 pi is a full revolution in radians. And so if you rotate the picture a full revolution, you have the original picture that you started with. The x-coordinate and the y-coordinate are exactly the same. So in other words, let's say that we are looking at theta plus 2 pi, which is the angle that when we measure it, we go all the way around and then by an extra bit by theta. And that's the exact same angle as simply going by theta. So that gives us that cosine of theta plus 2 pi is cosine and sine of theta plus 2 pi is sine. We say that the period is 2 pi. So period is whenever a function has an identity of this form, where variable plus a constant is the original function, then that constant is the period. Let's go on to our next geometric-based identity, and this one is negatives of angles. So in this case, we're going to see that cosine of minus theta is cosine. So cosine does not care about the it only cares about the absolute value of the angle, so to speak. And sine, when you give it a negative angle, the whole value becomes negative. So cosine is known as an even function because you can negate the input and get the same value. And sine is an odd function, which means that if you negate the input, the entire value becomes negative of what it was. So where do these come from? So the geometric idea is that if we measure our negative angle, so we go from the x-axis clockwise instead of counterclockwise, then we get cosine of negative theta and sine of negative theta, just by the definition of our cosine and sine functions. But then if we flip this whole picture over the x-axis, then we get the basic picture for cosine and sine. And what is the relationship between the x-coordinate of the original point before flipping and the x-coordinate after flipping, and also the y-coordinate? So for the x-coordinate, it's exactly the same. The x-coordinate, if we do our flipping, we go along this vertical line to get the other point. However, the y-coordinate is negative of what it was after flipping. And so if we link these facts together, we have that cosine of negative theta is cosine, the x-coordinate is the same, and sine of negative theta is negative sine of theta, which is that the y-coordinate becomes negative after flipping. Okay, what is our next geometric identity? This one is rotation by a quarter turn, pi over 2, also known as 90 degrees. So in this case, cosine of theta plus pi over 2 is negative sine theta, and sine of theta plus pi over 2 is cosine of theta. So to figure this sort of thing out, we need to understand what happens to coordinates when we rotate the plane by 90 degrees counterclockwise. So for sake of example, let's just look at the point 2, 1. It's as good of a point as any, and with it we can see the pattern. So let's take that point and rotate it by this pi over 2, which is a right angle. And if we plot it, we can see we're at the point minus 1, 2. So one striking thing here is that the numbers in this new point seem to be related to the numbers in the original point, and we could guess that, well, the new x-coordinate, well, I mean, there's no guessing here, it's minus 1, but we might say that that seems to be negative of the y-coordinate of the original point, and the y-coordinate of the new point, 2, appears to be the x-coordinate of the original point. So this is true in general. This is how rotations work. The new x-coordinate is always negative the old y-coordinate, and the new y-coordinate is always equal to the old x-coordinate. So with this in mind, let's plot an angle theta and also an angle theta plus pi over 2 for this 90-degree rotation. So for just the angle theta, we have the original point, which is cosine theta sine theta, and we also have the new point, which is cosine of theta plus pi over 2 sine of theta plus pi over 2. And applying rules I and II, we have, first of all, that the x-coordinate of the new point is negative of the y-coordinate of the original point, so we get negative sine theta, and also that sine of theta plus pi over 2, the new y-coordinate, is equal to the old x-coordinate, cosine of theta. So that's where that identity comes from. So using this identity, we can, for example, derive identities for rotation by pi. We could also work this out by pure geometry like before. But so let's see how we could apply rules I and II here to do a rotation by pi, a rotation by 180 degrees. So cosine of theta plus pi can also be written as cosine of theta plus pi over 2 plus pi over 2, because pi over 2 plus pi over 2 is equal to pi. So we have one example of an angle plus pi over 2 here, and so if we apply rule I, we get negative sine of whatever remains after removing that last plus pi over 2. And then this is an angle plus pi over 2, so we can apply the second rule, because that involves sine, to get negative cosine here. So we picked up this first negative from the first rule, and then there's no additional negative from the second rule. So sine is very similar. We take sine of theta plus pi. We write pi as pi over 2 plus pi over 2, which allows us to apply first the second rule to get cosine of theta plus pi over 2, and then the first rule to get negative sine of theta. So summarizing, when we rotate by a full pi, or a full 180 degrees, cosine becomes negative of what it was, and sine becomes negative of what it was. In our graphs of sine, something to keep in mind is that sine looks like this, and that is a 2 pi period, where then it repeats the picture from 0 to pi over 2 pi throughout the rest of the graph. And then right in the middle is that pi, and this second rule is saying that what's going on in this region from pi to 2 pi is exactly negative of what happened from 0 to pi. So that's why you get the same picture, but upside down when you shift the graph by pi. Another rule that we can come up with is using just what we have so far. and again, we can use geometry to come up with this one, but I want to show how to use these identities, is what are the rules for complementary angles? So let's start with cosine of pi over 2 minus theta. So just to remind you, what is a complementary angle? Two angles are complementary if their sum together is a right angle. So if I have an angle theta, its complementary angle, so the angle with which they form a complementary pair, can be written as pi over 2 minus theta. Okay, so we have got pi over 2 minus theta. And then I want to apply the reflection over the x-axis. I want to make the theta become positive, so what I'll do is I'll pull out the minus sign and turn it into theta minus pi over 2 being negated. And as we know, cosine is even, so cosine of negative that is just cosine of that. Next, I'm applying these rotation by pi rules. So I can add in pi to the argument of cosine at the expense of making cosine negative. And then pi minus pi over 2 is pi over 2. And finally, I can apply one of the rotation by pi over 2 rules. And cosine of theta plus pi over 2 is negative sine of theta. And we get a double negation, which cancels out and gives us sine. Similarly, for sine of a complementary angle, we do the first trick again, create this minus sign by negating what's inside. Sine is odd, so we can pull the minus sign out, and then we can use the rotation by pi rule, so that just makes sine negative when we add in a pi to the argument. The double negation cancels out, and then we can apply the rotation by pi over 2 rule to get cosine of theta. So cosine of the complementary angle is the sine, and sine of the complementary angle is the cosine. In fact, that is why it's called cosine. It's the complementary sine. It's the sine of the complementary angle. At least that's historically where it came from. Okay, so this was a few basic trigonometric identities. In a future video, we'll go on and explore some more of these. I'll see you later. Bye.